wireless magnetic power bank.
Wireless magnetic power bank? How does it work?
It's apply magnetism on this device.
Magnetism?
Yes. It's wonderful, right?
I think I want to grab it.
But how? Let's explore the use of magnetism in inductive charging.
This is a diagram of a magnetic wireless charger. A magnetic wireless power bank is a portable charging device designed to wirelessly charge smartphones and other compatible gadgets. Unlike traditional power banks that require cables, this device utilizes electromagnetic induction to transfer energy. The inclusion of magnets ensures precise alignment between the power bank and the device, optimizing charging efficiency. There are a few components of wireless charger. First, lithium-ion battery. This is the primary energy storage unit within the power bank. It stores electrical energy typically range from 5,000 mAh to 20,000 mAh, which can be used to charge external devices. Secondly, wireless charging coil. Transmitting coil. Located inside the power bank, this coil generates an alternating magnetic field when an alternating current AC passes through it. This magnetic field is essential for transferring energy wirelessly to the receiving device. The third component is magnetic ring. It is surrounding the wireless charging coil. A series of magnets are arranged in a ring formation. These magnets serve to align and securely attach the power bank to the back of the smartphone, ensuring that the transmitting and receiving coils are perfectly aligned for optimal charging efficiency. The next one is printed circuit or SMPP-PCBA. This port houses the electronic components that control the power bank's operations, including voltage regulation, power management, and safety features like overcharge and short circuits protect. The next one is USB ports like Type-C or Type-A. These ports allow for wired charging options, enabling the power bank to charge devices that may not support wireless charging. And the last one is casing. The external shell protects the internal components. It is often designed with materials that allow for efficient heat dissipation and may include indicators like LED lights to show charging status.
This is use of magnetism in the wireless charger. How magnets are used in this device? Firstly, alternating current AC in transmitter coil and alternating current flows through a coil inside the charging pad. This creates a time-varying magnetic field around the coil according to Ampere's law and Faraday's law of induction. Secondly, magnetic field induces current in receiver coil. When a compatible device like a phone is placed on the pad, the changing magnetic field passes through a second coil, the secondary or receiver coil in the device. According to Faraday's law, this induces an alternating current in the receiver coil. Next, rectification. The induced AC in the receiver is sent through a rectifier circuit which converts it to direct current DC. Finally, battery charging or power supply. The resulting DC is used to charge the battery or power the device directly. The type of magnet used in this device is electromagnets, and the role it plays is for the energy transfer via inductive coupling. Wireless chargers use electromagnetic waves to transfer energy between two coils, transmitter and receiver, through inductive coupling, and then two resonating coils. One coil is in the charging pad station and the other is in the device. They interact through an alternating magnetic field to transfer energy.
Importance of magnetism in device. Why? Magnetism is essential. Magnetic field generated by the electromagnet is essential for transferring energy wirelessly via inductive charging. Without a functioning electromagnet, the charging pad or device won't be able to create the necessary magnetic field to induce the current in the receiver, resulting in no charging. What will happen to this device if magnet doesn't function properly? First, there will be no magnetic field, because the electromagnet is the core component of the inductive charging system. If it's missing or failing, there will be no magnetic field to transfer energy. Second, it will affect the inductive charging, because wireless charging relies on the principle of electromagnetic induction, where the changing magnetic field induces an electric current in a nearby coil. The last one, it will affect the potential hazard, will give potential hazard. In some cases, a failing or malfunctioning electromagnet might also lead to other issues such as overheating or damage. Lastly, let me tell you the specific features that depend on magnetic properties in this device. It is the built-in magnet. Why? It is because it will perfectly align with the phone for ensuring optimum energy transfer. Second, it will ensure the power bank stays connected to the device.
There are a few applications of inductive charging. First, smartphone charging pads. Many modern smartphones support wireless charging using inductive charging pads. Users simply place their phones on the pad and the charging process begins automatically. 2. Electric toothbrushes. Some electric toothbrushes come with inductive charging stands. Users place their toothbrushes on the stand and the battery gets charged without any physical connection. 3. Electrical vehicles. Drivers can park their cars over charging pads and the batteries get charged wirelessly. 4. Medical industry. Inductive charging is being explored for medical devices like pacemakers, eliminating the need for invasive battery replacement surgeries.
The significant use of magnet in this device. First, enhancing coil alignment. Permanent magnets such as those used in Apple MagSafe technology assist in precisely aligning the device with the charging pad. Second, improving transmission efficiency. Magnet can increase the magnetic flux between the transmitter and receiver coils, enhancing the mutual inductance and thereby improving the overall power transfer efficiency. Third, reducing energy loss. By directing the magnetic field more effectively, magnets help in reducing energy loss due to misalignment or stray fields, ensuring that more power reaches the device being charged.
Is the impact of the magnet on society or technology. First, in healthcare and medical technology, for example, in medical imaging, advanced magnets in MRI machines offer clearer images and faster scans, improving diagnostics and reducing costs. Next, computing and electronics, for example, in quantum computing, 2D magnetic materials are foundational in developing quantum devices, potentially revolutionizing data processing. Lastly, infrastructure and mobility, for example, maglev trains. Magnetic levitation enables high-speed trains with reduced friction, offering efficient transportation solutions.